Hello friend, in today's lectures we are going to discuss about the shear stress equations which is used to calculate the shear stresses in the beam for the various sections like rectangular sections, circular sections, symmetrical I section, unsymmetrical I sections, T sections. Now let's see the shear stress equation. Let's see. Figure shows a simply supported beam carrying a UDL throughout the span. For this UDL, shear force and bending moment will vary along the sections of the beam. Consider here two sections AB and CD at a distance delta x, and we consider here elementary area, that is EF, which having the distance y from the neutral axis, and elementary area we say that is a dA. According to this, bending moment and shear force varying from point to point. So here we are considering two sections AB and CD. So on that section AB, M is the bending moment, F is the shear force acting at section AB, and sigma is equal to bending stress acting at that section AB, and it is varies from point to point. So another point we are considering here CD, and at that section CD, M plus dm bending moment is acting, F plus df shear force is acting, and sigma plus d sigma bending stress is induced or acting at the section CD. So according to our Flexural equation says that M upon I is equal to sigma upon y. So first we consider that section AB. So for that section AB, sigma is equal to M upon I into y, cross multiplication, say equation number 1. Similarly, section CD. For that section CD, stress formula becomes M plus dm upon I is equal to sigma plus d sigma upon y. So therefore, sigma plus d sigma is equal to, you may say, M plus dm upon I into y, say equation number 2. Now force acting on that section AB, force is equal to our basic equation, stress into cross sectional area. So force acting across AB, we may say that is FAB is equal to stress into area. So FAB is equal to, stress is equal to sigma, and here area we are saying that is dA is the elementary area. Similarly, force acting across the section CD, so FCD is equal to, we may write here sigma plus d sigma into dA. Now net unbalanced force on the strip EF, on the strip, so we may say dF is equal to difference between these two. So you may write FCD minus FAB. So therefore FCD sigma plus d sigma into dA minus sigma into dA. In that case, sigma plus d sigma, from that equation we may put M plus delta M plus upon I into y, and sigma is equal to M upon I into y. So M dm upon I into y into dA minus M upon I into y into dA. After solving this, you will get here df is equal to dm upon I into y into dA, that is the unbalanced force acting on that section AF, that is DF. Now total force F above the neutral axis, we can calculate that dimensions above the neutral axis, that is d by 2. So we may integrate this above equation, means these equations between 0 to d by 2. So instead of that, df 0 to d by 2 dm upon I into y into dA. So you will get here F is equal to dm upon I into y into dA. Now in that case, y into dA, that is, you may say 0 to d by 2, you may write that is the first moment of inertia, that is equal to a y bar. So F is equal to dm upon I into a y bar. Say equation number 4. So F is equal to dm upon I into a y bar. We have seen this equation number 4. Now shear force, general equation of that shear force is equal to shear stress into area, or you may say shear area. That is the basic equations for that shear force. So shear stress, that is tau, and shear area, from that figures we may say B into dx, that is the shear area. That equation number we may say 5. And for equilibrium conditions, both the equations, equation number 4 and equation number 5 must be equal. So you may say equating equation number 4 and 5. So dm upon I into a y bar, that is the first moment of inertia, a y bar, tau into B into dx. Now we have to calculate here shear stress. Tau is equal to dm upon I into a y bar divided by B into dx. So rearranging this, dm upon dx into a y bar upon IB, but dm upon dx is equal to force, or the you may say that is the shear force, which is denoted by F or sometimes S also. F or S, that is called shear force. So tau is equal to F a y bar upon IB. This is the shear stress equation, and in that case F is equal to shear force at the section in Newton, A is equal to area above or below layer under the consideration, y bar is equal to distance of centroid of area under consideration from neutral axis, B is the width of the section, and I is the moment of inertia of section about the neutral axis. Remember here, for moment of inertia we have to calculate every time moment of inertia about the neutral axis of whole section.